Since the middle of the 1990s, astronomers have found well over 2,000 planets and planetary candidates. And as they began to find these planets, the vast majority of the ones they found were Jupiter-like planets, large gas giants orbiting around distant stars. And what was interesting is that the types and the characteristics of these planets were not what astronomers were expecting. And just to give a little bit of picture of what they were expecting it to look like our solar system. That we were imagined to be just one of an ordinary, our solar system was just kind of a run-of-the-mill, ordinary type planetary system that as we looked out and found planets orbiting other stars, everything we found was going to look kind of like ours. And so it's helpful to see what our solar system looks like to get a comparison or to get a feel for just how different these other planets can be. And so if we look at our planetary system, we have 8 planets. We have the 4 rocky planets, Mercury, Venus, Earth, and Mars. They're orbiting close to the Sun. We've got the 4 large gas giants, Jupiter, Saturn, Uranus, and Neptune. They're further out. And we expected that as we were going to find planetary systems, that this is the way they would all look. And if we kind of take a more bird's eye view of our solar system, we'll find some even more characteristics that are important. That if you look at the inner part of our solar system here, inside this little fuzzy yellow ring, that's where the 4 rocky planets are. The orbit of Jupiter is the orange or the yellow red ring in this first diagram here. And you can see these are all nice circular orbits. In fact, as we pan out, except for the orbit of Pluto, which is shown on here, back when we thought it was a planet, all of the planets have nice circular orbits except for possibly Pluto. And again, they're nice and concentric. They all line up well with one another. And then as we continue to move further out, we find objects that have very eccentric orbits, these so-called Kuiper belt objects that orbit quite a ways out, more distant from the Sun. And then as we pan further and further out, we even get out to the Oort cloud, which is a repository or place where there's a bunch of materials that can feed comets into the inner part of the solar system. And so as we looked for planets outside our solar system, we had expected that we were going to find things that looked very similar to our home solar system. And in reality, when we got out and began finding planets outside our solar system, what we found was something very different. Now, a lot of the planets we've discovered, again, are Jupiter-class planets. These are found, this is because most of the techniques we use are far more sensitive to large, massive planets because they either dim more light when you're using the transit technique, or they have a greater gravitational tug when you're using the radial velocity technique, or they have a greater lensing when you're using the gravitational lensing technique, or they're just brighter when you're using the direct imaging technique. So finding massive planets was not so much of a surprise, but what was very interesting about these massive planets is that we found a lot of them that were orbiting very close to their star. And they all have very circular orbits. Now that's not incredibly surprising, but how circular they are was kind of surprising. In fact, as we looked at a lot of these planets, Jupiter orbits out about 5 astronomical units. It takes about 12 years to orbit. Earth orbits at 1 astronomical unit. It takes 1 year to orbit. A lot of these planets we were finding were orbiting down at fractions of an astronomical unit, or fractions of the distance between the Earth and the Sun. And in fact, what we found is that a lot of these planets had a orbital period, or it took days, a few days, 1, 2, 3, 4, 5, 6 days to orbit around their host star. And so this is something very different than what we find in our solar system. But beyond just being different, what's remarkable about these is that these Jupiters, or hot Jupiters as they're referred to, could not have formed in this place, so they had to have formed somewhere else and migrated into the inner part of their planetary systems. Now what that means is that has implications for what sort of rocky planets or Earth-like planets we might find. Because if we go look, where could these Jupiter-type planets have formed? Well, how you form a Jupiter-type planet is that it's got to have a rocky core, and then it's got to accrete a bunch of snow and ice and ultimately gas. And so the problem is that very close to the star, the temperatures are so hot that the ices and the gases are all driven out further out into the planetary system. So the Jupiters must form much further out, or these gas giants must form much further out. In fact, in our solar system, the closest place where Jupiter could form is about where it is. And so as we're looking at these planetary systems that have these large Jupiter-type planets that orbit very close to their stars, what we see is that they had to form quite a ways out, and then they migrate into the inner part of the solar system. Now you can imagine what that would do to the rockier planets as they're forming. The Jupiters are a lot larger. They're going to cause a lot of gravitational disruptions. In fact, they're probably going to kick most of the planets out of the solar system or put them into very eccentric orbits, either of which will make them no longer candidates for any sort of life. But astronomers were realizing, hey, as we have this migration happening, it's possible that the migration could happen quickly enough that then the planets could form afterwards, or the rocky planets could. And so maybe as the Jupiters migrate in, they stir things up, and then as things cool down, then the rocky planets form. But again, what we found kind of argues that that may not be the workable scenario, because not only did we find Jupiters with very close in, but we found them where their orbits were actually backwards of what we expected. Now, if we look in our solar system, the sun rotates in a certain direction, and all the planets orbit in that direction. And in fact, almost all the planets, except for those that have been hit and where we can account for reasons otherwise, all the planets spin in that same direction. What we were finding is that there are gas giants in these other systems where not only, or the gas giants actually orbit in the wrong direction, or with retrograde motion. Now, when we looked at how could we make these planets work, what we find is that the migration had to have happened over much longer time scales, and in fact in such a way that as the Jupiter is migrating in, its orbit actually gets flipped around onto the other side. And this takes a lot longer. It takes so long, in fact, that no planets could form afterwards. So while we haven't developed a complete and exhaustive list of planets, one thing that is very true is that as we've gone out and looked, we found a whole lot of ways of making planetary systems that look nothing like our solar system. Now, as a caveat, it's important to remember that we're not yet capable of detecting our solar system. So it may be that there are solar systems or planetary systems that look like ours. But what is definitely true is that the diversity and variety of planetary systems far exceeds what any astronomers even thought could be possible. In fact, it provides an argument that maybe our solar system and the way it looks is actually unique and rare. In fact, that it's put this way in order, or it was designed this way such that it would be a place where God could put life here. And so we find that as we increase our knowledge about these planets outside our solar system, we find that it's a reasonable conclusion to draw that God designed our planet and our solar system and our sun for the purpose of hosting life.